I'm going to take you into a website where I provided the link just in case you want to play along. What will be interesting to you though is if you play along with me, you're going to get different results than I get, right? Because this is using a random number generator to carry out a simulation. And so the results will be slightly different every time. So what we did in class is I asked everyone to flip a coin 10 times. Okay, the probability of getting ahead is 0.5. Okay, so that gets entered here. The sample size, I told all of you to flip it 10 times. Okay, so that's the sample size. And then there were probably about 20 of you present in class. So that's the number of times that this simulation was done. All right, and so this will do this for me. If I click run simulation, I was really surprised in class because everybody, oh my gosh, wow, this is pretty crazy data. Wow, I got some very atypical data here, which happens. I'm expecting most of you to get 0.5. That's the expected answer. And if you didn't get 0.5, most people got 0.6 or 0.4. This is incredibly unusual. This means that one person only got one head out of their 10 flips, and then someone else down here got 9 heads on their 10 flips, right? Very unusual. In this normally distributed data, now when I look down below, it's going to show me the standard deviation. This is probably going to be the highest standard deviation that I've ever seen from this experiment. Average that we got here is 0.53. So that must mean we've got more at the higher end than we got at the lower end. All right, because the average is a little higher than it should be. Standard deviation, I think in our class when we did it, and we got very little variation. Everybody either had 0.4, 0.5, or 0.6. Our standard deviation would have been less than 0.1, right? Because everyone was either within 0.1 of the average, or if you got 0.5, you were 0 away from the average. Okay, so our standard deviation would have been less than 0.1. Here it's 0.18. Okay, so much higher than we usually see. And if I look down at this graph, this is fairly close to a normal distribution. All right, these values over here at the extremes would be in the tails. And that's what we talked about in the last segment, that it's very unusual to get those values in the tails, but they do happen. And so again, this isn't perfectly normally distributed. And one of the things that I want to show you is what the result will be if I had you flip the coin more times. Okay, let's say I had you flip the coin 100 times. It's very unusual for someone to get 0.1 for their probability. That means that one head out of every 10 flips, right? So this person would have to get 10 heads, only 10 heads out of 100 flips, okay? It's more likely to get a crazy kind of result when you've only flipped the coin 10 times, right? By the time you flip it 100 times, those unusual results should get more balanced out. Okay, so what I'm expecting when I increase the number of times that we're going to carry out the experiment, I'm expecting my variability to decrease. All right, I'm expecting my standard deviation to go down. And I'm expecting the mean to get closer to the true mean. Okay, the true value that I'm expecting to get is 0.5. I expect that the more I carry out the simulation, the closer my experimental probability will get to my theoretical probability. Okay, and that's something we're going to define early next week. And we'll talk about something called the law of large numbers, that the more times I carry out the experiment, the closer the experimental probability gets to the theoretical probability. Because we have someone in this experiment thinking that the probability of getting ahead is 1 out of 10, right? That's their experimental probability. Okay, so let's run this simulation. And just as I expected, far less variability. That's because the number of times we carried it out went up. This looks much more like what we got in class when we did it on Wednesday. And again, I was very surprised by such low variability when we had such a small sample size. I did get closer to the expected probability, right? I'm still not perfect. And my standard deviation went way down. And let's take a look at this. Oh, this looks like a much more perfectly bell-shaped set of data. Okay. And the more times that I carry this out, I mean, this actually is a really good bell-shaped curve. If I wanted to really increase this number and say, hey, I want 50,000 people to come do this experiment. And look how fast it can complete 50,000 results. My mean is exactly what it should be. Now that's interesting. That's interesting that that happened. I should get a more perfectly bell-shaped curve with the more people I have doing the experiment. That actually didn't happen. I actually had a better bell-shaped curve when I had less people, which is not supposed to happen. But again, that's the thing with these experiments is that what's expected in theory and what happens in practice may or may not be the same thing. All right, because remember, the bell-shaped curve is based on a very, very large amount of data. So if you wanted to play around a little bit more, in class when we rolled the dice, and this, it was 1/6, which is 0.166 repeating. I asked you to do it 12 times, and there were about 20 of you in class. Okay, so here's some people. We were rolling for 4s, I think, in class. Oh my gosh, I'm getting crazy data tonight. Look at that. A couple people got 0s. This person got like more than half of their data was 4s. Again, pretty high standard deviation. If I increase this to 100 and everybody rolls the die 100 times, right, I'm going to get far less variation. Oh, I didn't hit run simulation. Right, the more times I carry out the experiment, right, notice my standard deviation went down and the average of the samples got closer to what I'm supposed to get in theory. So the experimental probability got closer to the theoretical probability. So we'll talk a little bit more about this. Wait, let me go down here and look at the bell-shaped curve. So again, kind of not a perfectly bell-shaped distribution of data. Okay, it approximates a bell-shaped curve, but it's not perfect. So let me see if I can make my point better that didn't get made in the last example because things just didn't fall the way they were, quote, supposed to. If I change that to 50,000, I should see, right, because I have a larger amount of data, I should see, yeah, there we go. Look at that beautiful bell-shaped curve. That's what's supposed to happen. The larger amount of data, the more likely I am to get a perfectly bell-shaped curve. And that's a pretty much perfectly bell-shaped curve. So thanks again for watching. One more video to go today.